I'm John, the CEO of Veridise, and I'm here with Rami, a senior protocol engineer at RISC Zero, and today we're going to talk about zkVMs and zkVM applications.
Yeah.
Thanks for making the time to chat with us.
Thank you so much for inviting me. It's great to be here.
So why don't we start by just having you explain what is a zkVM, and specifically some more information about RISC Zero's zkVM.
Right. So zkVM, short for Zero Knowledge Virtual Machine, right? And you can do a lot of things with that. So a zero knowledge proof in general is more of like a generalization of signatures, right? So in a signature, you have a private key, a public key, a verification algorithm, and a signing algorithm. And then you have a varying message, right? And if you know the private key, you're able to produce a signature with the signing algorithm on a certain message. And anyone who then attains that signature and uses the verification algorithm along with your public key is confident that that signature came from someone who knows the private key, right? When you go to a zero knowledge proof, you sort of generalize that one more level where the private part is no longer a fixed format key. It can be any kind of input. The signing algorithm can be generalized to any program you want. And the signature is a zero knowledge proof instead of the cryptographic signature. And then you also have the output of the program. So you get a proof that gives you confidence that only someone who knows the input to the program that would cause it to actually give you that certain output is able to generate this proof. And the RISC Zero zkVM is unique in the sense that it was the first general purpose zkVM, where you were able to specify any program you liked, compiled down to the RISC-V instruction set architecture. So using a standard instruction set architecture was the huge unlock for RISC Zero, because it meant you had control flow, you were able to write most programming languages, regular programming languages, instead of a DSL. And that was a huge unlock for developers who basically did not have to learn SIRCOM or deal with restricted circuit width or height when dealing with their inputs and how long their computations were supposed to be. And that was RISC Zero, essentially. Unlimited compute, or run arbitrarily long programs in ZK and prove whatever you can easily express in general purpose languages, mostly Rust.
Yeah. So let's zoom in on that a little bit. So you mentioned, because you have people running their programs in the zkVM, they now can write general purpose programs that then are executed on the VM, rather than having to learn a new language like SIRCOM or Halo 2 or something like that. Can you talk a little bit about how this helps developers and, kind of like a little bit more about the developer experience or the benefits?
Right. Well, from personal experience, right, it's a huge leap forward for development. I've back in 2017 or 18, I was writing R1 CS circuits in C++ by hand. It was, what you can do now in RISC Zero in maybe a weekend, you had to spend maybe a month or two to put together, and then it's just very hard to ensure that it's bug-free or actually works. And that's the huge unlock for developers. You don't have to deal with writing very fancy constraints in hard systems, or using a specialized DSL that might be harder to work with than a general purpose language. You can just express the computation you want in a language like Rust, for example, which is our main focus, and have that work directly in the zkVM. It's also important to note that you can do things that are very simple, like loops and conditions in very simple ways as you would normally do them, and then the VM would execute as long as it needs to get your computation done.
And I think one of the other really cool things that we've seen a lot is, you don't really need to write anything special. The way that you format a zkVM application in RISC Zero is, fairly familiar. There are a couple of things that you have to know, but then you also get access to all of those like Rust crates that
Exactly.
you wouldn't have to before, and then you can just go ahead and
Yeah.
use those however you want.
Yeah,
It just
exactly.
makes building some of these applications much easier.
Yep. Yeah, you just import your favorite crate, and it's mostly going to work out of the box unless it depends on some obscure assembly instructions that are hard-coded in, and then those can't be compiled down to RISC-V. That's the only practical obstacle. Otherwise, yeah, it's very easy to work with.
Yeah. So let's focus a little bit on the zkVM itself. And so the zkVM is obviously a ZK circuit. It does all of the hard parts. So when you have a ZK circuit, obviously it comes with several benefits like privacy and stuff like that. But it also comes with challenges. And so one thing that we've looked a lot at Veridise is whether some of the challenges that you have in ZK, like privacy leaks, underconstrained circuits, stuff like that, are inherited by a zkVM application. So what guarantees does the zkVM itself give you so that now developers don't have to worry about it?
Right. So one nice thing about the RISC Zero zkVM is that we know it is actually ZK. Right.
Mm-hmm.
It is one of the few VMs out there that actually gives you a ZK guarantee. And what that means is the adversary or the verifier doesn't actually learn anything about the trace of execution of your program. So all these intermediate steps, they're actually perfectly hidden from the adversary. So you can, feel safe that if some private piece of information is accessed in a certain step, nothing is going to leak about that info, as long as you don't output it directly in the program. Right, and that's the important part. You have the VM giving you ZK over your program for free, but you have to use it right. It's not like you can just throw anything into the VM and then feel secure. You have to, just like with signatures, you have to sign the right messages in the right sequence in a certain protocol. You also have to make sure that the output that's coming out of the zkVM is meaningful for the system that you're building and doesn't leak in itself something about your private data, or doesn't underconstrain the input that it receives. So while the circuit also has to deal with ensuring that it's not underconstrained and is fully secure, you also have to ensure that your program makes sense in that same way.
Yeah, so let's narrow down a little bit on the underconstrained input part. So can you elaborate more on what exactly you mean by an underconstrained input?
Mm-hmm. Well, let's take Ethereum block execution, for example, right? The EVM is a pretty fancy construct that relies on a lot of things. And let's say you want to prove the execution of an EVM block.
Yep.
You can do that pretty straightforwardly using Revim, the REVM crate. Essentially, and Revim only asks, as it executes the transaction, that you just give it the values of the storage slots that it's looking at. It doesn't actually authenticate those itself. So a naive ZK EVM implementation would be to throw Revim into the zkVM and only provide the storage slots, right? If you want to do it right, where you're actually giving a meaningful proof about what the result is of the execution, you would also have to implement your own way of authenticating the storage values that you pass into Revim. So you'd essentially verify the Merkle inclusion proofs against the state trie of the Ethereum block you're executing to make sure that if someone malicious were to run this program, they wouldn't be able to forge any storage values. They would be forced to only provide as input the correct state of Ethereum.
Right. And so, yeah, this is one thing that we have to look for a lot with these zkVM applications, is making sure that any information that's accessed within the zkVM is somehow flowing to the public outputs somehow, to make sure that someone at the other end can validate that this is correct. And the case that you gave is a really interesting one because you've got all of this information in a block, but it's basically just a summary, and you have to do so much computation to make sure that summary is actually accurate, or validation to make sure it's accurate. But once you do, you can just output that block hash, and then you have a good summary of exactly the execution environment of the state.
Yeah, exactly. Flowing is a very nice word to use.
Yeah.
Yeah, you have to make sure that you're authenticating everything from start to end.
Yeah, yeah. Let's move a little bit into privacy. You touched a little bit on this. So if someone wanted to build an application that requires privacy, they could do so in RISC Zero.
Yeah, of course. Today, if privacy is a concern of yours, you can do it, but you have to take care of where you generate the proof, right? If all the input is public knowledge, it's fine. You can delegate that proof to any party. You can do it with a decentralized network like Boundless, or you can do it with a centralized service like Bonsai. Both are from RISC Zero. But if you have private input, you have to take care not to leak, the private aspect of that input to any external party that you don't trust.
Sure, sure. And so in that case, if someone did want to use a proving network, or they felt like they needed to use a proving network because their computation took a while and they wanted to make sure that it was sufficiently fast, let's say, does that mean that they wouldn't be able to use RISC Zero and they instead would have to write their own ZK circuit? Or is there a way to, still get privacy while using a proving network?
While using a proving network, well, while using RISC Zero, the prover itself, you can of course use that to attain privacy as much as you want. Everything is fully open source, so prover, verifier, you can take everything and run it from start to finish on your own hardware that you trust. The nice thing about the RISC Zero prover is that you can configure it to work on your machine, basically on your laptop, proving, unlike some other systems. Take circuits, for example. The bigger your circuits, the bigger your memory requirements for proving. But because the RISC Zero, the VM circuit itself is fixed, it's actually very small. It's not too sizable. You can configure the prover to only use very small memory. For example, it can run on as little as 4 to 6 gigabytes of RAM, I believe. So if you want privacy, you don't have to look for another tool. You can build using this, and you can let your users fully prove their own transactions or their own programs locally on their machines.
Privacy is super important in some applications, and like people, I'm sure, are going to use RISC Zero for scalability, but it's also important to think about some of these privacy applications and how they might also be able to get some benefit out of this. I guess, given that you do work at RISC Zero and work with a lot of people who are building on top of your zkVM, and you yourself build on top of the zkVM, what are some applications that you can see coming out, or you have developed, that maybe previously weren't possible or too difficult to do?
Well, one thing that I'm very passionate about is layer 2 systems. And one thing that we've recently developed that wasn't exactly possible before are ZK fault proofs. And ZK fault proofs that actually work, in the sense that they can withstand attacks by very powerful or very wealthy adversaries. So ZK has been a huge, and specifically the RISC Zero zkVM, because of how much it can compute in a proof, has been a key unlock of that. Previously, all systems for fault proofs, ZK or not, were very restricted in certain ways, and you'd measure their security by considering a situation where you have a very wealthy whale adversary who perhaps has 1 million ether to burn to attack your rollup and try to land a faulty sequencing proposal.
Sure.
Before we developed Kailua, which is our ZK fault-proof system for rollups, All the other algorithms would require the defender of the rollup or the honest party in the protocol to basically perform a move for every move performed by the adversary, or lock up more collateral as they perform these additional moves. So it means that if someone has more money than you, they can just overwhelm you and cause you to lock up so much collateral you just run out of funds chasing after them, right? Or spend so much in transaction fees that maybe they just get ahead of you at some point and you're out of money. You can't really chase after them in the interactive protocols anymore. The nice thing with Kailua is that's no longer necessary. All you need for safety is to just have one single honest party make one single honest transaction that just proposes a valid sequencing proposal. And because of ZK, we've made the fault-proof system non-interactive. And no matter how much computation is needed to run in the VM to get that fault-proof done, the RISC Zero zkVM can do it. And that has been a previous restriction where talking to other protocol designers, right, people who've made very prominent fault-proof systems, they've always considered ZK as expensive or something that should be used very minimally or in the worst case, right? When you look at Kailua, it actually throws the entire block execution and derivation process into the zkVM and uses that as its basis for security, along with some other nice ways to make the adversary shoot itself in the foot when spamming the chain to attack you. So that's the core, right? You have a reliable zkVM that you can use and you can count on even if you want to prove a few trillion cycles worth of execution. Of course, in normal CPU terms, a trillion is nothing, right? We have we have regular CPUs that run in gigahertz, and that's fine. But for when you're looking at a ZK program, this amount of execution just wasn't possible before in ZK, before the RISC Zero zkVM. So having something you know is essentially boundless, which is you can rely on. It really helps you design some solid protocols because you just don't have the same restricting assumptions as before.
So let's talk about Boundless really quick, since you've brought it up a couple of times.
Yeah.
So, we've talked about, people being able to run a zkVM on their own machine and it being performant, but also these proving networks. And so, what is the intended user base of the proving network, and how do you guys plan on doing this decentralized proving that you're talking about with Boundless?
So Boundless is similar to a marketplace, right? Okay. But it's not in one place. Boundless will work on any chain that can support this set of smart contracts. And Boundless basically connects seekers or people who are requesting proofs or seeking proofs with provers who are able to catch those requests, fulfill them, and give the verifiable proofs on chain. And it's a huge enabler for block space, essentially. You can, if you look at the current status quo, block space is very restricted, either because of block size in raw megabytes or block size in the sense of execution, because security here just depends on the propagation speed of blocks. So Boundless is a way to give you basically more execution without changing the security of the underlying chain. You do introduce the cryptographic assumptions that come with the ZK proofs, but you don't really change the consensus layer in any meaningful way. And it's more about making block space abundant instead of scarce. And it's not exclusive to any one chain. You can seek proofs on one chain, use them on in another chain. But that's the core unlock, making block space essentially boundless.
And by making block space boundless, you essentially mean making the compute that you can have in a block boundless, compute. Right?
Yeah, exactly.
Yeah. And so then you mentioned a little bit about what was the terminology? Seekers, and the other side was
Provers.
Provers, okay.
Right.
I wasn't sure if you had
Yeah.
another term for provers. So essentially, the provers will be bidding to prove or
Yeah.
generate your proof.
Right.
And so that's where it's like an auction, right?
Yeah,
and
and
so
that's-
anyone, if they had sufficient compute, could become a prover
Yeah.
and then could, generate the proof for you.
Right, and the nice thing about it is that it's set up in a way that you actually, as a user or as a seeker of a proof, you get the best price possible, because it's up to the provers to lock in a price in the auction, or lock in a certain price in a range that you define, and you get the best price that's available amongst these proofers. So it's very efficient for the user, and that leads to very efficient price discovery in the auction mechanism.
Yeah. So we talked a little bit about Boundless and how RISC Zero can help with L2s. Maybe let's move on to a little bit of something more related to security. So if someone wanted to integrate RISC Zero into their protocol, how do you think that would impact the security of that protocol, or what impact do you think that might have on the security of the protocol?
Well, I mean, depending on the existing trust assumptions, right? It could be just introducing additional trust assumptions, or actually removing some of them, depending on how bad your protocol was in terms of that. But like, what example of protocol do you have in mind?
Well, yeah, I mean, basically what I was curious about is, there are some cases where you do have some fairly strong trust assumptions, because even though we are, in a space that loves decentralization, there still are a lot of centralized entities like bridges and stuff like that. And so it seems like there's a lot of applications available for zkVMs, because now, at least, if you're executing something in a zkVM, you have that cryptographic proof, and it actually removes quite a few trust assumptions. I mean, in some cases, maybe it does add trust assumptions, but I think that really the main trust assumption that's added is that the zkVM is implemented correctly.
Right, and the cryptography checks out. Right?
Sure,
Sure,
but
and all that. Yeah, the proof system is fine. Yeah. But bridging
that
is
still comes down to the zkVM being safe. Yeah.
Bridging is an interesting example, right? Especially, completely cross-chain bridging, like for example, between Bitcoin and Ethereum. Because you are always going to need certain trust assumptions there for the consensus to happen, or for the synchrony between both views of the chains to happen, right? But what you can reduce is the worst case scenario, the cost of the worst case scenario, when someone is trying to, just as with rollups, convince one chain that another chain is in a certain state.
Sure.
Right? And because of the scalability properties of the zkVM, you can provide very short summaries of the execution that happened, and prove that the state being reported is actually, by someone, is actually valid and not invalid. So you can, discard some of the concerns you'd have to address by just getting integrity guarantees.
Right, and so making more secure clients basically on chain.
Which makes your job much easier, honestly, as a protocol designer.
Yeah, of course. I mean, there's so much interest in interacting with different chains like Bitcoin, and we've seen a lot of different ways where people, try to do that. But it would be just a lot easier if they had stronger guarantees and didn't have to worry quite so much about, the potential for the local version of the local representation of Bitcoin diverging from the actual Bitcoin blocks. But
Like clients are useful everywhere, basically, bridging, even on your phone, if you want some actual guarantees about the state of the chain. Not a lot of wallets actually try to authenticate anything that gets reported by the RPC.
Really?
Yeah.
Okay. So we touched a little bit about how one of the trust assumptions, or the main trust assumption that you have when interacting with the zkVM, is just the safety of the zkVM itself. So this is the underlying cryptography, the implementation of the circuit, and so on. And so what does RISC Zero do in order to help make sure their zkVM is secure?
Auditing is one thing.
Sure.
Yeah, we have very clever people. People try to audit the zkVM, and formal verification is also a very important endeavor there. And I believe we've been one of the, I would say, well, we've been spending a lot on attempting to formally verify our zkVM in the sense that we'd like to make sure it's deterministic, most of all, and that it complies with the actual RISC-V spec.
Right.
And it's been a handful of tools combined to try to achieve those goals. And it's been a very long-term effort, as you know,
Yeah.
to get there.
Yeah.
Yeah, and that's good because what that gives you is basically an algorithmic guarantee that this code actually realizes this specification,
Right.
and it's no longer that someone just has to, trust me, bro, on on the whole implementation flow.
Yeah. And at least as the company verifying the determinism, that is very important, especially as you guys continue to make changes and optimizations, because it is a very important property to make sure that, the actual VM is deterministic, like RISC-V itself.
Yeah.
But you also mentioned earlier, like making sure the underlying cryptography and stuff like that was sound. So are you guys also doing any work on ensuring that, you're using the best cryptography, the best constraint system, the best proving system? I know that you guys implemented your own intermediate representation, and so
So Jeremy, our chief scientist, now chief executive officer of the company, is really the powerhouse behind all of those things. He's been keeping track of ZK for so many years, and RISC Zero didn't really come about except after many, many iterations by him to get it to be performant enough or secure enough. So we really keep up with all of the research. We have dedicated people to reading up on all the latest papers quantifying what their impact may be for our proving system, because we don't, a lot of new things come out and they're very hyped up, right? But once the proving pipeline is pretty big. It's bigger than one component. So once you try to fit that component within your pipeline, you might find yourself losing a lot of properties. Like, one important thing in the RISC Zero VM is that it scales out in terms of proving as much as you want. So the more machines you have, the faster you can make proving go.
Okay.
And there's no restriction on that. It's essentially like running a MapReduce computation to get all the proving done, right? Some proving systems aren't very friendly to that in terms of how much the distributed provers would have to communicate with each other to get that going, or in terms of how good the recursion would work to compress the proof.
Okay.
So there are very practical considerations that you have to keep in mind when adopting different things in the proving system. And we try our best to stay up to date with everything coming out.
Yeah. And when you said that you're essentially doing a MapReduce, it's because basically when you execute an individual instruction, that's kind of a proof on its own that you can allocate to an individual prover, and so it becomes this kind of embarrassingly parallel problem, and then you just need this recursive circuit to come and make sure all of those instructions are consistent and wrap everything up, right?
Yeah. What we do is basically we split up the entire trace into segments, and then every segment is proven on its own and then recursively reduced to a single proof, essentially. And we don't actually it's not a uniform prover or a uniform circuit doing both the recursion and the instruction proving. We have a circuit for recursion that is very small, very efficient, compared to the RISC-V circuit, which is in charge of the individual segments and making sure that each instruction is correct. So
all of that just sound, it's very complicated for sure. A lot of distributed computing, and then you mentioned earlier that you guys have also worked on hardware acceleration and stuff like that as well. And so I assume that based off of the configuration of your system, if you have access to multiple machines or just like GPUs, it sounds like you could just allocate a proof to whatever resources you have, take advantage of as much parallelism as possible in order to generate proofs quickly.
Yeah, GPUs are the perfect environment for our prover. We don't target CPU proving at all, so you'll find that pretty inefficient if you're using RISC Zero. GPUs shine when you use the RISC Zero prover.
Okay.
And it's because of this embarrassingly parallel property that it's very convenient to just have the GPU try to parallelize all the computations.
Okay.
Yeah. Even proving multiple segments in tandem if you have enough memory in the graphics card.
Yeah. So where do you think, let's say that you could use or you could build anything with RISC Zero. Is there something that you think is that you would want to build, or that you think is, kind of something obvious that should be built with it?
Yeah. Well, yes. But it's a very expensive thing. Fully homomorphic encryption, right? It's already expensive outside the zkVM.
Right.
If you throw it into the zkVM, it gets much slower.
Okay.
Right.
So what's the benefit of doing fully homomorphic encryption inside of the zkVM, since you already have, privacy from, the zk component?
So it has to do with the secure delegation that we spoke about, right? Let's say you want to securely delegate the proving to another party. If that party only gets to see encrypted inputs, they don't really learn anything about your private information, essentially. Now, the output would also be encrypted because that's how FHE works, right? But then you'd be able to just take that very simple, very small proof, combine it and prove locally that you know how to decrypt the output in that other zkVM receipt. The receipt is just our name for the combination of the proof and the output. And then show what you want to reveal about the output that you received. So it really helps with the secure delegation. But of course, it's it's something I'd love to see happen practically. It's just...
So that's in that case, the zk component is just used in order to provide certification, but and so that's why you kind of need both, right? So the fully homomorphic encryption brings the privacy element. You can have encrypted inputs, but then if you just used fully homomorphic encryption, you wouldn't get the certification component. So that's why you need those two elements. Okay.
Yeah, FHE on its own doesn't give you a guarantee that the computation was run correctly. There are ways to do it, but they would really, they're also very inefficient and they're not very general purpose.
So at RISC Zero, you spend a lot of time thinking about zkVM applications, obviously, and building zkVM applications. So what advice would you give to developers when they, start thinking about designing a zkVM application and, actually work on implementing it?
Well, to be frank, just make sure you really need zk, right? Sometimes you might feel it's a really cool tool that isn't really applicable, and that will just give you a lot of pain. When you know that zk is the answer, that's when you can build the best application, basically, because you'll be using the correct tool for what you need. So that assessment is very important. I've often spoken with a few people who believe zk would help their application, but it's actually not what they're looking for.
Would you be willing to give a few examples of that?
Well, one example, one that's still left in my head is an example with one student of mine, like a year ago, and he was looking to do a very complicated MPC protocol. I don't remember the specific details, but he wanted to add zk to a certain part of the pipeline while he was actually getting what he needed for free from using MPC.
Sure.
He just had to, shuffle around a few responsibilities in what each party was doing. That was it. That was what really, drove the point home for me. It's not, it's not always. I wanted to promote, of course, the use of zk to him, but he had all he needed. I wasn't doing him any favors pushing zk onto him.
So in that case, what you're saying is just zk didn't add anything. It just made the system more complex.
Yeah, and worse performing.
Yeah.
But when you know that you need it, you can do the really cool things, like what we did with Kailua. Like, for example, what Eigen and Celestia are doing with their DA. It is sometimes the best tool to use in terms of scalability. Advice for people to make their things more secure? And actually, like, what's your take on it?
I mean, we've already touched on this a little bit, and so there are several things that we've seen happen with zkVMs. So we already touched on, missing validation on inputs, and so you called it an underconstrained input. We normally just call it a validation error. And so in that case, someone makes some assumptions about the input, but because the values are being provided by an untrusted entity or an entity that you shouldn't trust, that can lead to, proving computation that the user didn't intend. And so ensuring in some way that any aspect of the data that you're relying on can somehow be validated, either on-chain or within the zkVM itself, is very important.
Yeah, I don't think there's a generic general formula, right? You just always have to make sure that you're getting the plumbing right from input to output.
Yeah, I mean, really, the way that you can kind of think about it, though, is there has to be, or in many cases, there should be data that flows from the input. So if you trace the information flow, there should be some flow from the input to the output. So all information should flow from the input to the output in many cases. There might be some cases where that doesn't hold, but so far, in most of the ones that we have looked at, that is a fairly important property. Another thing that we've seen is we've already touched on privacy a little bit, and so there are some cases where someone does have input that they don't intend to reveal, and in that case, ensuring that private inputs don't flow to public outputs is important, but also ensuring that people can't learn about those the value of those private inputs some other way by kind of gathering facts about other pieces of data to cobble together information about that, or something about that private information. And then I guess another thing that we've seen is just the interaction with the on-chain component, or issues with the interaction with the on-chain component. Because if someone is going to be checking in the proof on-chain, which many of the people building things with RISC-V eventually will do, or RISC Zero eventually will do, they need to ensure that, one, and typically a proof can only be accepted by the smart contract once. There are some cases where maybe it can happen multiple times, but those are few and far between. Normally you want to ensure that a certain action is only taken once you get a proof. Otherwise someone can just, obviously spam that with the same proof. And then the other case that we're looking at are cases where a proof that you receive from RISC-V might appear to be different if you're just looking at the hash of the proof, all of the information that you receive about the proof. So like if you're trying to take in the proof itself as a nullifier, or treat the proof itself as a nullifier, there are cases where someone can manipulate the input data and very slightly modify the trace in some way that doesn't actually impact the computation, and therefore the proof itself doesn't end up being a nullifier. And so if someone did think, oh, I can just use proof uniqueness in order to ensure that no one is going to make or replay my proof, that's not actually going to work.
Yeah. And even if there's some randomization in the proof system, for the sake of ZK, for example, you would get a different proof for the exact same trace.
Yeah.
But of course with the same output and the same security guarantees.
Right. Right. And so ensuring that, people have thought about also constructing proofs that make sense, or proofs that they can actually verify and are what they intend on chain is another important thing that we've seen.
Yeah, it's interesting that you mentioned that, because we also have a product called Steel that allows you to make verifiable view calls,
right?
Proofs of verifiable view calls, right? And the output of Steel always contains a certain block hash, and that means that this proof is only valid if you're able to verify that this block hash is still part of the chain or is part of the chain.
Right.
It can get tricky because you can only look at the past
Yeah.
256 blocks. But yeah, you can also use the beacon chain to have a reference that's valid for a day. And yeah.
Light client for your own
Yeah.
for your own blockchain. But
Yeah.
yeah. Steel is an interesting case because when you guys put out Steel, that's something that we audited, but it's actually just a library for people to build on, and it provides them the tools that they need in order to interact with Ethereum without actually needing to go and implement the complicated validation that we talked about earlier, that all of the data that you have in your block hash actually is consistent. And so Steel lets you prove some really interesting things on chain. I'm curious if you've had anyone who's kind of approached you about some use cases or ways that they intend to use Steel.
Yes, so one client of ours is actually generating a proof that would have otherwise cost them, I think, 10 billion gas on chain to compute.
Okay.
Just iterating over an entire list of wallets that have a certain token and deriving some properties off of them. In a regular view call on chain, that would be millions of dollars in gas. In compute, I think it was $10 or so at the time. It could have been smaller.
Okay.
It could be smaller now. Yeah.
Wow. Okay.
Yeah. Unless you really scale things. And we have some new features that we're adding in, like verifying receipts and events that happened on chain instead of just issuing view calls. So being able to basically validate that any kind of event happened on chain, right? Whether it's some transaction taking place and causing some kind of state change or otherwise, because developers, it's good to streamline things for them on the ZK side. Right.
And I can imagine that, there are some cases where that would be very useful. Like you said, there's a state change that someone wants to recognize. Like, with a lot of these centralized bridges, the way that they work is they emit an event to say someone actually deposited and this is where they want the money to go. And, they wouldn't really have to modify much of their infrastructure at all because now they just have a ZK circuit that says, did this event happen? Yes, I can prove that it happened. And then you check that in on the other side. So that's really cool.
Exactly.
Yeah.
I think also another interesting thing is side channel attacks. It's interesting because we have accelerators, precompiles for the zkVM, where certain cryptographic operations are made to be as efficient as possible within the zkVM. So it really makes you want to reduce the cycle count as much as possible, or the circuit size in case it's a parallel circuit. Which means you're not going to care about constant time guarantees anymore.
Right. And I mean, that's a good point, but I think having constant time guarantees is hard no matter what, because since the input to your zkVM is no longer a straight line program, which is something that you have to have with a ZK circuit, then you can have timing channels inside of the application itself, because if they just take a different trace through that program, that can reveal information. And so that's where the timing information could be used to reveal information. So the very, famous or the easy example of this is when someone tries to check a password and they just keep checking until they find the first character that's wrong and they return. And then you can time it in order to see how many characters you got correct and then iteratively figure out the password. But constant time is going to be hard to do for developers as well, and not only just for you guys on the prover side, because there's been research that's shown that there are microarchitectural impacts, or there can be specific microarchitectural implementations in floating point computations and stuff like that. And under certain values, some things might be faster. And so
Yeah.
it's going to be difficult to provide any sort of constant time guarantees. And that is something that someone has to be aware of if they are interacting with the zkVM and want to have privacy.
Yeah. It also gets much more exacerbated in the zkVM because the time difference between proving, for example, 1 million cycles and 10 million cycles, which could be the time difference in certain cases in encryption, for example, or signing, will be very much expressed much more heavily when you're computing the proof, right? It's not about like nanoseconds or microseconds anymore. It's about maybe a minute or so.
Yep. It's going to be interesting to see how many people, or for how many people, these timing channels are actually going to matter, because you can reveal some interesting information from a timing side channel, but I think that if someone, like, there are ways that you can protect against them on both the prover side and the application side. So on the application side, people just have to write constant time code. And then on the prover side, I guess the way that people normally try to mitigate some of the side channel impacts is by adding random delays to when information is returned. I guess, is that something that you guys have been thinking about when it comes to creating this proving network, or actually running your own provers?
Well, I mean, to be honest, no, we're making them go as fast as possible. No random delays. That's goal
Maybe
number
it'll
one.
just be a specialty feature, like you want it to be side channel free. We'll turn a knob, we'll turn down the performance for you.
Yeah, worse performance as an added feature is
exactly.
not,
Yeah, you just gotta sell it right. More security, worse performance.
Yeah.
What's next for RISC Zero? I know that you guys are releasing Boundless later this year. Are there any other interesting developments or things that you guys are working on?
We've been very focused on Boundless, essentially. We've basically designed some very interesting primitives that we want to get out there to incentivize provers and make the market very efficient. For Boundless, a lot of extensions are planned. It's not going to be RISC Zero exclusive, actually. We do plan to add in support for other zkVMs to join once their tool chains have basically matured enough to be able to be part of Boundless because of the primitives I mentioned. I can't reveal too much about them, but they're very essential to making provers and seekers just meet at agreeable terms. But we've maybe not been highlighting this enough, but we do have a very strong performance roadmap planned for the zkVM itself. We've recently gone into an exclusive deal with Binius, for example, the team behind Binius, to integrate Binius into the zkVM, which will allow very interesting hardware provers to come out that can make very good use of the binary fields that Binius uses. And we also have...
So by hardware provers, you mean ASICs?
ASICs,
Yeah,
exactly, yeah. Because we're using GPUs, FPGAs don't really give us a very significant boost.
Okay, yeah, that was going to be my other question, is if it's specifically ASICs, or if you're also, talking about FPGAs.
No, it's you get very good. The team has run some internal tests. We've seen as good as 30x improvements just by using that prover. So that is one jump, aside from all the other optimizations that we're doing to the zkVM itself and the additional precompiles coming out. You've come across Zergen, of course, right? Going through. Yeah. It's what the circuit's written in.
We audited your circuit, and we're verifying its constraints. So of course we've come across Zergen.
I'm just, I'm not part of the process. And you were just writing a ton of precompiles for cryptographic tools and search in. So
I know that you guys are wrapping up Keccak, and then
Mhm.
do you have any others coming out soon?
Keccak is actually part of the release right now. You can
Mhm.
use it live. We're wrapping up the formal verification of Keccak
Mhm.
soon. And also the BN254 accelerator
Okay.
precompile for for pairings, BLS 381 as well for all the KZG related things.
Right.
Yeah, then some other interesting precompiles that should make certain programs that do a lot of certain operations much faster.
Sure. Yeah. I mean, that's the way precompiles work.
Yep.
So yeah, that'll be interesting to see them when they come out. I
Yeah,
guess.
and
Yeah.
we have a second version of our circuit coming out soon.
Oh, really?
Yeah, it is going to give much better performance.
Yeah.
We've seen 2 to 3x across most programs.
Mm-hmm.
So that is also going to be a pretty good jump that's
Right.
coming out soon.
Right. Yeah. 2 or 3 X's.
Yeah.
Pretty significant.
Yeah,
So yeah, that's exciting. But I guess thanks for joining us
Thank you
and
for having me.
telling us about everything going on at RISC Zero and
Yeah, well, not everything. but,
well,
you know.
everything that you're allowed to talk about at
Yeah.
RISC Zero, and hopefully no more. I hope we didn't get you into trouble.
I hope not. We'll see in the
Yeah.
editing, hopefully.
Yeah, it would be really unfortunate if the talking with the security company was the security leak, but
Yeah. Fortunate for me as well.
But
Yeah.
no, this was fun.
It's been a pleasure.
Yeah. Thank you.
Thank you for having me.
Yeah.
Yeah.